Hello students, I am here again with some questions in optics which carry 3 marks. Some of them are mathematical, these are very simple and not very long. I will give answers in some questions, but in some of them I will give you hints only. So begin with question number 1. Find the expression for the equivalent focal length for a system of two thin lenses in contact. For answer of this question, you have to derive the expression 1 by f is equal to 1 by f1 plus 1 by f2, where f is the equivalent focal length of the combination of thin lenses, which is also expressed as f is equal to f1 into f2 by f1 plus f2. The derivation you can find in the lesson of refraction by thin lenses. The second question is, for a prism of a small angle A, derive the relation between angle of deviation delta and refractive index of the material of the prism mu. The derivation for the answer of this question is very easy, and that you can get in the lesson refraction and dispersion through prism. The final relation is delta is equal to mu minus 1 times A. Next question is number 3. When a white ray of light passes through a prism, it is dispersed. Why? Why does violet color deviates most but red color deviates least while dispersed by a prism? For this question I am giving you the answer. When white ray of light enters the prism at some angle and refraction takes place at the surface of the prism, all the constituent colors move with different velocities. The refractive indices of medium of the prism are different for different colors, and therefore angles of refraction for different colors are different. Hence dispersion of white light occurs. And for the second part, the color having longer wavelength moves faster than the color having shorter wavelength. We know that wavelength of violet is smaller than that of red. Hence, violet color takes longer time to reach the second refracting surface of the prism, where it deviates furthermore away from the normal. Therefore, violet color deviates the most, but red color deviates the least when dispersed by a prism. There is one more question similar to this. Question number 4. Why dispersion does not take place by a glass slab? I am leaving this for you to think about. Now see question number 5. What do you understand by the term interference of light? Mention the necessary conditions for sustained interference. First, you have to describe the phenomenon of interference of light, and then for the second part of the question you have to list up the conditions for sustained interference. If you go through the lessons of interference in wave optics, you will find the answers of both the parts. Next is question number 6. What is polarization of light? State and prove Brewster's law. Here I am giving you description of polarization and statement of Brewster's law. Derivation of the expression mu is equal to tan IP you can follow in the lesson of polarization of light. Polarization of light is the phenomenon of restricting the variation of electric field vector in a particular direction perpendicular to the direction of propagation of light. And Brewster's law states that when unpolarized light is incident at a polarizing angle IP on an interface separating air from a medium of refractive index mu, then reflected light is fully polarized with vibrations in the perpendicular direction of the plane of incidence, provided mu is equal to tan IP. Question number 7 is very easy. First, you see the question. What is the effect on the interference fringes in Young's double slit experiment when A. Distance between screen and slit is increased. B. Separation between two slits is increased. C. In place of yellow light, green light is used. You know the expression of fringe width in interference pattern, that is beta is equal to lambda capital D by small d, where lambda is the wavelength of light used, capital D is the distance between screen and the plane of the slits, and small d is the separation between the slits. Now you can very easily give the answers. For A, fringe width beta is increased with increase in capital D, as beta is directly proportional to capital D. For B, beta is decreased with increase in small d, as beta is inversely proportional to small d. And for C, beta is decreased when green light is used, as beta is directly proportional to lambda. And here, wavelength of green light is smaller than the wavelength of yellow light. Now see the question number 8. Why are coherent sources required to produce interference of light? How coherent sources of light are obtained for interference? One of the conditions for interference is that the two light waves must have same amplitude and same frequency or wavelength. The coherent sources of light can fulfill this condition as they have same amplitude and same frequency. Hence, for interference, coherent sources are required. To obtain two coherent sources for interference, two narrow slits are illuminated by the same source of light, and hence the secondary waves coming out of slits have identical amplitude and identical frequency or wavelength. Now we take up some numerical problems. So question number 9. Calculate the refractive index of the material of the prism when angle of prism is 60 degree and the angle of minimum deviation of the light ray is 30 degree. We know the formula for refractive index of the prism, that is mu is equal to sine A plus delta m by 2 divided by sine A by 2. Here A is equal to 60 degree and delta is equal to 30 degree. Substituting the values of A and delta in the expression of mu, we get mu is equal to sine 45 degree by sine 30 degree. The value of sine 45 is 1 by root 2 and sine 30 is half. So mu is equal to 2 by root 2, and therefore mu is equal to root 2, which is equal to 1.414. Next question uses Lenz's formula. The question number 10. An object is placed at a distance of 60 cm from a concave lens of focal length 15 cm. Find the position of the image formed and magnification of the lens. We know that the focal length of concave lens is negative. Here u is equal to minus 60 cm and f is equal to minus 15 cm. From lens formula 1 by f is equal to 1 by v minus 1 by u, we get 1 by v is equal to 1 by f plus 1 by u. Substituting the values of f and u, we find 1 by v is equal to minus 5 by 60, which is equal to minus 1 by 12. Therefore, v is equal to minus 12 centimeter. It means image is also formed on the left side of the concave lens. Now, magnification m is equal to v by u is equal to 1 by 5. You know magnification m is equal to h dash by h, the ratio of size of the image to the size of object. So here it is 1 by 5, which means image is diminished, that is of a smaller size, and the image is virtual as value of m is positive. The last question is number 11. In Young's double slit experiment, the slits are 0.03 centimeter apart and screen is 1.5 meter away from the surface of the slits. The distance between the central fringe and the fourth bright fringe is 1 centimeter. Find the wavelength of light used. Here small d is equal to 0.03 centimeter. D is given in centimeters, so you have to convert it in meter, which is equal to 0.03 into 10 to the power minus 2 meter, and capital D is equal to 1.5 meter. As 4 beta is equal to 1 centimeter, therefore beta is equal to 1 by 4 centimeter, which is equal to 0.25 into 10 to the power minus 2 meter. The fringe width beta is equal to lambda capital D by small d. Therefore, lambda is equal to beta into small d divided by capital D. And substituting the values and solving it, we get lambda is equal to 5 into 10 to the power minus 7 meter. It can also be expressed as 500 nanometer. That's all for today. I hope it will help you. You keep on practicing similar problems. Good luck.